Hi guys, it's been a while since I made a video, so let's see if I can do this in one fail swoop and do this right. If you're here, that's because you are following directions. Maybe it's because you struggle with that Beltwork. That was a tough Beltwork. There's something called equating coefficients right there. I'm going to talk about it here in a second. Then that's just going to lead us right into what we're doing today. Yes, we're going to take some notes today. I won't give you any stamp or new problems. I'm going to give you one problem to make sure you can practice and have it cemented in your brain. Then when I come back on Monday, we will work with it, make sure you did it right, and then we can actually expand on it. So this is like the nuts and bolts of this new idea. But first, I promised Beltwork. So let's look at the Beltwork. Very first one, hopefully you guys got a clear picture of this. If these two equations are equal, a lot of times we think of solving for variables as getting a variable by itself, but that's not always the case. And in this first Beltwork, and all three of these actually, I think this is number 4, we do something called equating coefficients. If I'm saying that the left side of my equation is equal to the right side, then that means the constant on the left has to be the same as the constant on the right. B is equal to 90. Done. Okay. The linear coefficient, that's what we call that because it's in front of the linear term here. The linear coefficient on the left has to be equal to the linear coefficient on the right. So A is equal to -11. That's it. Don't overthink it. We like equating coefficients. So let's take that same type of idea and move it down to the next one. Okay, so the quadratic coefficient, that's the coefficient in front of my x squared, has to be the same as whatever's in front of my x squared, my coefficient on the other side. So we get a little equation this time. We can say -2a equals 16. Oh, if that's true, then a equals -8. Hopefully some of you guys got that, okay? Continuing down the line there. The linear coefficient, 5b, on the left has to be the same as the linear coefficient on the right, -5. So if 5b equals -5, then b equals -1. Easy as that. Constant equals constant. -c equals 1. Sure, so then positive c would equal -1. Positive c equals -1. And we're dancing. Okay, the last one, it's definitely the trickiest, but we can handle it. It's not impossible. The quadratic coefficient, 5, has to be equal to all of the quadratic coefficients on the other side. So I have an a plus 2. And we get a little equation. 5 equals a plus 2. A equals 3. Okay. How about the linear coefficient now? 21 has to equal anything in front of the x. 4a plus b plus 10. Okay. 4a plus b plus 10. Okay. Normally we'd be stuck here, but now that we know what a is 3, I can plug that in there. I know that's 12. I can subtract the 12 to the other side. 9. I can subtract the 10 to the other side, and I get b equals -1. Finally then, the constants, right? Oh, that's it. It's a and b. There is no more constants. We could have done the constants to make sure it all worked, but we get -2 equals, what are the constants? 4b plus 2. Let's check it out. -2 equals 4b plus 2. Well, we already figured out that b was -1, so let's see if it works. 4 times -1, -4. -4 plus 2, -2. Yeah, -2 equals -2. We're just equating coefficients, okay? You guys can handle that, and we are going to need it here in a second. I try to keep these videos less than 15 minutes, so I may go a little bit faster. You may go zoom through this and change it to double speed if you are brave enough. I talk pretty fast as it is, but these are your notes. Do what you need to do. So, without further ado, our second to last topic, or actually this is our last topic before we test. It's called partial fraction decomposition, and it's actually not too bad once you get the hang of it. The math, not too bad, but you got to follow my instructions, and I'm going to teach you a shortcut eventually, and you got this. So let's see here. A fraction, we know what a fraction is. To decompose means to take it apart, or it decomposes into the parts that make it up, and then partially. So we're doing all this stuff. We're going to have a fraction that we partially pull apart. It's going to be handy for us sometimes in calculus to take apart bigger expressions into all the pieces that make them up. Normally, we've called that factoring. That's multiplication. But with partial fraction decomposition, it's going to be adding or subtracting. So I had a little neighbor talk here, if you want to take a minute, if you and your neighbor are doing this together. Why do people take engines apart? They like it. It's fun, sure. But also, to see the individual pieces. You take engines apart to see what's working and it's not working inside that big, nice machine that someone made for us. But when it's malfunctioning, what's malfunctioning? So if you take it apart, you can see all those pieces together. And that's what's going to happen with partial fraction decomposition. It's starting with a fraction and then working backwards and figuring out the two fractions that add together to get me that. We're pulling apart fractions. Well, it's not as easy as that. That looks pretty easy, right? Get a common denominator, 3, 6, 1, 6. Yeah, that is 5, 6. But it's going to involve some x's, right? We put this with rational functions for obvious reasons. That definitely looks like a rational function, division of polynomials. Our goal for these notes and for this section is to start with a rational function and to decompose it into two smaller ones. Okay, we got our goal out. Now let's go figure out how to do that. So the first thing I want to mention with this, one of the most important things when you decompose fractions, we are going to assume what our answer is going to look like. If I have an idea, if I'm dividing and I have these linear factors, we call these are both to the first power. If these are linear factors down here, then when I partially decompose this fraction, it's always going to be some constant, some number over x plus 1 over one of the factors, and then some other constant, some other number over the other linear factor. Notice above how we did this. If I add these, we would get a common denominator and add them. We would get this after getting a common denominator. For us, we're working backwards. I just need to know that when I decompose these, if this is to the first power, then in my numerator is going to be to the 0 power, which is just a constant. So we have to assume what our answer is going to look like. Well, one other notion I'll bring in right here. Partial fraction decomposition will only work when the numerator degree is 1 less than the denominator degree. If it's not, then you have to do long division to make it happen. So again, we talked about long division, then we've used it here these last couple days as a part of other things. So this is partial fraction decomposition. We have to assume what our answer is going to look like. And then from there, well, let's get going. What are we going to do from there? From here, if these two fractions were to be added together, you would need to find a common denominator, right? I can't add two fractions together unless they have the same denominator. That common denominator is this thing, x plus 1 and x minus 4. Well, this partial fraction, this fraction, is missing the x minus 4. So I would multiply the top and bottom. This one is missing the x plus 1. So I would multiply the top and bottom by x plus 1. And when we have that, through the miracle of technology, I've already done that, we get this mess. It's not too bad. It's okay. I have my initial fraction is equal to these two things now. All we've done is multiply by fancy forms of 1. Now here we get a little fancy with this. What we're going to do right now is multiply all three of these fractions, 1, 2, 3, by that common denominator. We're multiplying by the LCD. When you do that, it gets rid of them. At this point, we're basically ditching the denominators. Everything has the same denominator, so I don't need to look at the denominators anymore. If I had 1 over 7 plus x over 7 equals 5 over 7. They're all over 7. I don't need to look at the 7s anymore. I could just do 1 plus x equals 5, and x is 4, just like it was up there. It's the same thing here. Once we all have a common denominator, I can ditch those denominators. I don't even need them anymore. So I'm just going to write the numerators, and the numerators look like this. From here, we could equate coefficients, right? We just did that on Beltwork. I could multiply this out and get ax minus 4a plus bx plus b, and then equate coefficients just like you did below. But it's going to have that. You'll have to solve a system of equations, substitution elimination, which isn't the end of the world. We may have to do that anyways. But we have this new technique. This new technique is called convenient values. This equation that I wrote here with all these x's works for any x you want. It is true for any value of x that your heart desires. Well, guess what? My heart desires x to be 4. If I plugged a 4 in for all my x's, what we're going to see is 4 minus 4 turns to 0, a times 0 turns to 0, and I've effectively eliminated one of my variables, right? I said substitution elimination. This is a version of elimination. If I plug in a 4 into all these, I will be able to figure out what b is. And vice versa, I could also use -1. If I plug -1 in for all my x's, the x's, this one is going to turn to 0, and then I can figure out what A is. So I've done that down here. This is called convenient values. Hit pause if I'm going too fast anywhere. Go back, take your time, write it, try to figure out what I'm talking about. Talk with your neighbor. You guys are helpers here. So here's me plugging in a 4. I plugged in a 4, plugged in a 4. There's that 0 we talked about, and I'm left with B equals 3. Okay, cool. Next convenient value was -1. If I plug in a -1, this one's the one that's going to turn to 0. So that goes away. Now I'm left with -5A equals -10, -5, -10. So A would equal 2. Okay, so I made up some problem. I said, I think my answer is going to be A over x plus 1 and B over x minus 4. We assumed that form for our answer. So then once I found A and B, our final answer, don't spike the ball yet. We got to put B where B belongs, where A belongs, and then we get our partial fraction decomposition. And this is what we knew from the very get-go. The whole problem was, what does this decompose to? What does this decompose to? Well, we figured it out. It's 2 over x plus 1 and 3 over x minus 4. Okay? Try another example. We'll do this together. We have about 3 minutes. Hit pause. Go try it the best you can. If you get stuck, talk with your neighbor. If you both get stuck, then come back and hit play and we'll finish it. Okay, I don't know if you hit pause. I think you did, but maybe not. From this point, we talked about assuming what our answer is going to look like. The fact that this denominator has 2 linear factors is telling me that I'm going to have A over one of them, just some number over x minus 3, and some number over x plus 2. So that's what I have right there. Some number over x minus 3 and some number over x plus 2. Our next step was to get a common denominator. If I was going to get a common denominator by adding these 2 fractions, I would have to multiply the top and bottom of this one by x plus 2, A times x plus 2. Top and bottom of this one by x minus 3, B times x minus 3. Then everything would have the same denominator. Well, just like before, if everything has the same denominator, I can ditch the denominators. I'm left with this. Next, you could try to make a system of equations by equating coefficients, or we can do convenient values. Looks like plugging in a 3 would get the job done. If I plug in a 3, this turns to 0, and everything, those vanish, and I can solve this. How about this one? Convenient value. -2. If I plug in a -2 for all my x's, this one is going to vanish, and I can figure out what b is. So here's my work for plugging in -2. I get b is 2. Here's my work for 3. That's what a is. We put those where they belong for a and b, and we just did partial fraction decomposition. Okay, I'm down to 1 minute. That's good. I don't even need a minute. I'm going to give you guys one problem I want you to bring with you next time I see you on Monday. I want you to do a partial fraction decomposition for this guy. Figure out what that partial fraction decomposition is. Hopefully we have that. If it looks like a duck and quacks like a duck, it's probably a duck. This thing looks like it can be factored. It can be. You should factor this first so you can decide what form your answer should take. Okay, that's it. That's our video. Enjoy the rest of your Friday. Email me any questions you have. I'm out. Peace.